every exponential is a sigmoid looking backwards. And so this is exactly what happened with airplane speeds. I think in the early 1970s or late 1960s, people were booking flights to the moon based on the increasing trend of airplane speeds at the time. And then essentially all of a sudden, these increasing airplane speeds came to a halt. We had these saturated around the speeds that we have today.
One exponential which hasn't saturated yet is the cost of Search API access. But there's one exception. The Brave Search API is an affordable, independent search solution. The Brave Search Index covers over 20 billion web pages without the big tech biases or the extortionate recent price hikes. So what makes it unique? Well, it's powered by real human anonymized web page visits. So they're filtering out all of the junk data, and it's updated daily with tens of millions of new web pages. Brave is perfect for AI model training and retrieval augmented generation use cases. The data is sourced ethically and the prices are developer friendly. If you want representative data and up-to-date information, the Brave Search API offers both. So go to brave.com/API, check it out. They give you 2,000 free queries every single month. So you can go on there and you can see how good this index is. Enjoy the show.
I'm Sayash Kapoor. I'm a PhD candidate and a researcher at Princeton University's Center for IT Policy. And I'm currently finishing up my PhD at the Department of Computer Science.
And you're working on this really interesting book, right?
Yeah, the book is called AI Snake Oil. And we try to delineate between applications of AI that work from those that don't. And we basically want to offer readers a way to cut through the hype.
Yeah, I've been looking forward to this book for months now. So hopefully I can get a pre-release copy, and I'd love to do another conversation about that because I'm really excited about that.
Absolutely.
Amazing. Okay, so I want to talk about your article that you just released on your Substack. But just before we get there, I mean, how seriously should the government take the threat of existential risk from AI?
So the threat of existential risk, I think, is sort of a once-in-a-lifetime event in some sense. And to some extent, I think we've seen policymakers adapt to claims about existential risk, both from prominent AI researchers, but also from communities such as the AI safety community, the effective altruist community. And so to some extent, I think the response is reasonable. It's an event that can only happen once, so we only have one chance to get it right to some extent. And in the article, we try to go over what the arguments for existential risk are and how seriously we should be taking these arguments. And we in particular look at one of these arguments, which is the probability of doom or P-doom, which has become like rampant, not just in the tech community, but also in the policymaking spaces in the last couple of years.
Interesting. So you made the argument essentially that these risk, probabilities are too unreliable to inform policy. Can you elaborate on that?
Yes. So when we are coming up with probabilities for any event, I think there are basically only three ways to go about it. We can come about it inductively. That is, we look at past events of a similar sort that have happened. We can come about it deductively. That is, we have a theory for how the world works, and then we apply the theory to make predictions. Or, as has become the norm in the AI community, we can come about it subjectively. Now, let's set that one aside for the moment, and let's dive into inductive and deductive probabilities first. So in terms of inductive probability, you can come up with great probability estimates for the risk of, let's say, car crashes by looking at like a person of a certain type who drives a certain type of car, lives in a certain neighborhood, etc. Insurance companies regularly price products like car insurance premiums. And I think more or less that seems to work well. I mean, there are some nuances about bias and risks of discrimination. But apart from that, like let's say if car insurance prediction is 20% off, that seems all right? We cannot do that for AI risk simply because there is no past evidence for this type of work. We don't have a reference class, so to say. And so any probability numbers that we come up with based on past events are extremely speculative. Now, to be clear, this reference class is a spectrum. So certain things can happen multiple times, many millions of times, and we have extremely precise reference classes, if you will. So like when you toss a coin, we have a very clear reference class, and we can predict that the probability of a fair coin will be, let's say, 50% landing as heads and 50% tails. We might have reference classes that are somewhat more vague, like the car insurance example. And then in typical probability estimation of events, The extreme end of the spectrum is things like geopolitical events, where you have the risk of war, and the reference class is past events of a similar nature. So past wars that have broken out, past famines that have led to political instability, and so on. Now, compared to this entire spectrum of reference classes, AI risk is maybe completely outside the spectrum, or at like an extreme end of the spectrum, to the extent that a reference class just does not exist. Now, people have tried to come up with reference classes, and I'll share some of them just to show how absurd these reference classes can be. One example is the risk of various animals going extinct. Another reference class is past sort of changes to the Earth's atmosphere, past waves of extinction that we've seen. And hopefully it's clear how very different all of these types of risks are compared to the risk of us losing control over AI or power-seeking behavior emerging in superintelligent systems or all of the other hypotheses. So it is on this basis that we reject the idea that we can come up with reference classes, and therefore we can come up with inductive probability estimates of the risks of AI doom. So that leaves us with deductive estimates of probability. Deductive estimates are those where we have a theory that we have validated in some real-world setting, and we seek to apply it to this other real-world setting. And we have faith in the theory simply because of it being validated and us making assumptions about the scope of this theory. And now this is all a little bit abstract, so let's get concrete. One example of X risk that's not from AI is existential risks from asteroid impact. So we might be concerned that when an asteroid of a sufficiently large size, let's say, collides with the Earth, there would be enough energy generated that it could sort of clog up the atmosphere and block off all agricultural production. Now, how can we come up with a deductive theory for this? Well, we have evidence from a large number of smaller asteroid hits as to what happens when an asteroid collides with the Earth. And based on this theory, we can sort of extrapolate to what would happen when a large enough asteroid hits the Earth. And again, I'm drawing from other theory about what would happen and how much energy would be needed to sort of block off the production of agriculture in the world. We can then come up with an estimate for how big an asteroid needs to be and how often these big asteroids do flybys close to the Earth to see what the probability estimates of or the p-doom of asteroid impact is. We have no such theories for existential risk. People have tried to come up with theories. One theory is that once the number of computations in an AI system equal the number of computations in the human brain, that's when we'll have transformative AGI. But that tells us nothing about whether this AI is likely to lead us to sort of the lack of control scenarios that are talked about. But more importantly, this assumption itself is extremely tenuous. We don't understand as well right now whether this is precisely what leads to intelligence, whether there are other factors. In fact, I would say many neuroscientists would vehemently disagree with the fact that the number of computations is what leads to intelligence. And now this brings us to sort of the final part, the part that I set aside for the moment. So lacking either inductive theories, so a reference class for making inductive probability estimates, or deductive theories about how AI risk might come about, what the community has largely turned to when forecasting the risk of AI extinction are subjective probability estimates. Now, what subjective probability estimates do is that they sort of feed into our cognitive biases to take quantification seriously. So I think all of us have many cognitive biases. Quantification bias is the tendency to take events that are quantified more seriously than ones that aren't. And so when someone says that the p-doom or the probability of extinction from AI is 15%, we might take it more seriously than we would claims about, the risk of AI going rogue being high. And I think if we look at all of the evidence that the community making predictions about AI doom have given us, the underlying reasons for these probability estimates are extremely tenuous. So one of the most important, I believe, prediction tournaments that happened recently was the Extinction Prediction Tournament. It was carried out by Philip Tetlock and his colleagues, and they basically asked, 100 or so AI researchers, as well as super forecasters, that is, people who had excellent records at forecasting events in the past, to participate in a prediction tournament, that is, to predict the possibility of X risk. And it turns out that if you look at the reasons that people gave to justify their abilities, those reasons are no better than what we might expect from anyone like on the street who is thinking about AI risk. Reasons included things like, well, maybe AGI would decide to colonize space instead of the Earth, and so they'll reduce their AI dome risk, and so on. And so what we really take issue with is dressing up these feelings as numbers and making it seem as if there is a precise estimate behind claims that there is a high risk of extinction from AI.
So your article argues that there are many reasons why these risk estimates might be, systematically inflated. I mean, can you tell us about some of those reasons?
Absolutely. So when we look at the metrics that are used to evaluate these forecasters, we find that they severely overestimate the probability that events that might not ever happen or might happen very infrequently, also known as tail risks, in a systematic fashion. So in the blog post, we do an analysis of one such example. So let's say we have two forecasters, forecaster 1 and forecaster 2. Forecaster 1 always makes the correct probability estimate based on their prior. Forecaster 2 makes the exact same estimate, except if the risk is less than 1%, they always predict the risk to be 1%. So in some sense, forecaster 2 is overestimating tail risks. That is, they're overestimating all risks that have a less than 1% probability of occurring. Now, if we assume that the probability distribution is uniform, and we want to find out which of these two forecasters is better, can you take a guess as to how many forecasts it would take for us to get an estimate of whether forecaster 1 is better than forecaster 2? It turns out to be in the hundreds of millions, and that is for the simplest scoring rules, the scoring rules that are not so sensitive to overestimating tail risks. If we look at scores like the Breyer rule, for example, the estimate is closer to 1 trillion. So in other words, it would take us 1 trillion observations to be able to tell if forecaster 1, who is predicting, let's say, a probability of 0.0001, is better at forecasting than forecaster 2, who just says a probability of 1% to tail risks.
You mentioned the dangers of utility maximization when it comes to X risks. How should policymakers approach this problem without falling trapped to Pascal's wager? And if you wouldn't mind, could you explain what Pascal's wager is?
Absolutely. So Pascal's wager is this very interesting thought experiment about whether one should believe in God. So it states that one should always believe in God, because if it turns out that God does indeed exist and one does not believe in God, there's an essentially infinitely negative utility function to that call, because it's like an infinite life in hell. Whereas, so if there's even a small possibility that God exists, one should always believe in God. So this is an example of the dangers of utilitarianism in dealing with making consequential decisions. Because let's take the example of X risk. What if we try to estimate the utility, the expected utility of existential risk, even if we have a very low probability? Now, some of us, and like reasonable people, might conclude that the cost of humanity going extinct is essentially infinite. There's probably nothing worse that could happen. And therefore, if you have even a very small probability that is non-zero, that humanity goes extinct, you're incentivized to always do everything in your power to stop existential risk. So if we were to take this seriously, if we were to adopt a purely utilitarian expectation maximization theory and apply it to real world decisions, all policymakers would ever do at any given point of time is talk about X risk.
By the way, your blog is amazing. These guys have got the snake oil blog on Substack, and it's probably my favorite blog that I read on Substack. And so I was reading back a little bit. But you had one about AI scaling myths. And let's start with, how do scaling laws compare to other scaling plateaus, like airplane speeds, for example?
So there's a strong tendency in the field of AI, in some parts of the field of AI, but more broadly in the field of people talking about AI, to assume that exponential trends can hold indefinitely. I think very recently I read this piece called Situational Awareness that draws these trend lines that go all the way up to the right and argues on this basis that we'll get to AGI sometime very soon. Now, our piece on AI scaling myths was not a direct response to the situational awareness piece. A lot of people thought it was, but we'd actually been working on it for a little bit of time. But essentially, if we look back at the history of what happens to things that people have thought are exponentials, what happens when we sort of look past let's say, the first few years of this type of exponential, we've found that people have largely been disappointed. I think there's a saying that goes, every exponential is a sigmoid looking backwards. And so this is exactly what happened with airplane speeds. I think in the early 1970s or late 1960s, people were booking flights to the moon based on the increasing trend of airplane speeds at the time. And then essentially all of a sudden, these increasing airplane speeds came to a halt. We had these saturated around the speeds that we have today. And the reasons for that were a little bit technical, a little bit business related, but essentially it shows the perils of thinking that trend lines can continue forever. I think there are always bottlenecks that arise when previous bottlenecks are fixed. And that's how we've also seen progress in AI. If we go back, 50 years, in the last 50 years, we see that AI progress has been a punctuated equilibrium. So every time we have a new paradigm, there's a lot of resources, a lot of intellectual as well as material resources that are spent in improving this paradigm. And this is how progress takes place until we've saturated a paradigm. And once we saturate a paradigm, there is essentially a period where we're looking for the next paradigm, and progress sort of slows down. It becomes the sigmoid, not the exponential anymore.
Just a quick digression on that situational awareness piece. I mean, as you can guess, I'm not a big fan of it. And to me, it represents the worst of Silicon Valley groupthink. But do you have any comments on that?
I mean, to be clear, I don't think that the piece is awful. I think it makes for entertaining speculation. But I think it could be harmful if we don't treat it as such. Yeah. So I think if we look at sort of these predictions about the future more as science fiction and less as what's actually going to take place, I think they're perfectly harmless. So the piece in and of itself seems completely harmless to me. What then becomes harmful is VCs taking this seriously as a means to allocate funding, as a means for prioritizing what products actually get built in the real world. And I think that's where the groupthink comes in. And I do think this is a strong tendency, because I was reading a report that said half of VC money in the last year was spent on generative AI. And at some point, I think as a community, VCs have to think about whether that's really the best allocation of their own money, but that also of the best way to spur up innovation. Because any singular VC, of course, wants to maximize the returns on their investment. But as a community, there's also the question of spurring innovation on an ecosystem level.
Yeah, I agree with your take. I mean, I'm in the UK, and certainly in the outgoing government, the policymakers were taking that kind of thing very seriously. So that this is very, very important. But shifting a little bit, do you think we're going to see a shift to smaller, more efficient models?
Oh, absolutely. I'm a big fan of efficiency. I think one of the best ways to make actual real progress in the real world today is through models that we can run multiple times, let's say for the same task, models that are within reach for smaller developers, for tasks that might not require the best model, actually, tasks that can be accomplished by smaller ones. And in some sense, I think we're already seeing this trend. We've seen that the frontier models for literally every single AI company today are not their most expensive models. So GPT-4o is less expensive than GPT-4 Turbo and GPT-4. Gemini 1.5 Pro is less expensive than Gemini 1.0 Ultra. Claude 3.5 Sonnet is less expensive than Claude 3 Opus. And so in some sense, it seems like companies have also started to see the value in reducing the cost and making things more accessible. And another step on that trend is that companies are releasing even smaller versions of their frontier models, which I think is extremely promising. So, I mean, writing the blog is only a small part of the work I do. I also do a lot of AI research. And having access to cheaper models that we can use for solving real-world research problems is something that has greatly improved the accessibility of this research in my own work as well. So we're developing agents, we're developing benchmarks. All of this is aided by the fact that, GPT-4o costs a tenth of the cost of GPT-4.
Yes, and I'm really interested in your agents paper, and we'll get to that shortly. But just before we move on, though, a good digression here is, what do you think of the commercial LLM ecosystem? What are the dynamics there?
I think that's a great question. And it's an interesting time to think about this question as well, because for a period of time between 2023 and earlier this year, GPT-4 was undoubtedly the leader in the space. There were questions around whether OpenAI had something special. OpenAI had done something that no one else had been able to reproduce. There were questions around, GPT-4 itself being special. So, GPT-4, in some cases, in the communities that we were just talking about, was seen as the model that is helping OpenAI do a lot better, and they're integrating it in their own workflows and so on. I think we can fairly say that today, I think it is a repeatable process. It's the outcome of good engineering and good data. And so as a result, GPT-4 is not really special anymore. We have models from at least 3 companies that are as good as or better than GPT-4 in most tasks, including in coding, reasoning, writing abilities, and so on. And so that puts us in a very special place because we have seen these companies, and the companies themselves have seen themselves as building gods to some extent. The promise is that we'll bring safe and beneficial AGI into this world. But increasingly, it seems like these companies are building products. These are products that can be commoditized. Meta actually has explicitly and openly said that they want to commoditize their complement, and that's why they're releasing these models openly. And so when we have open models that are widely available to the general public, that are as capable as GPT-4, I think a lot of the myth-making around large language model goes away. And essentially, the way in which we should look at them is much more as consumer products competing in an open market, as opposed to products or like companies that are going to get us to safe and beneficial AGI, whatever AGI means.
Yeah, I mean, I agree that the AGI delusion is fading away, and I agree with the shift to products. I think part of the thing is originally companies thought that LLMs were their meal ticket, and that's all they needed to sell. And they're not as general as we thought they were. And also, when you do software engineering, reliability engineering is an ongoing concern, right? You have, you're fine-tuning models, you're adding data in, you're testing. When you put them into production, they suddenly surprise you and do things you don't want to, even if you're building RAG systems, information retrieval, in the enterprise was already a costly endeavor. You've got security problems and all sorts of stuff. And you can't just rub magic LLMs into it. It's a very difficult thing, and they're not really helping enterprise solve those problems.
Yeah, absolutely. I mean, I think with the introduction of Search GPT, I think OpenAI was also made keenly aware of the problem. So I think we've essentially had no companies that have used LLMs to create search products that have in their demo videos not had hallucinations sort of ruin the show for them.
Yes, indeed. What do you think is the role of synthetic data?
I think synthetic data is important insofar as it can be used for specific capabilities, for improving the data generating pipelines, for rephrasing things in ways that make the LLMs perform better. But in general, synthetic data has been made out to be far more than, at least I think it is. So I think there's been speculation that synthetic data will be the only thing we need in a very short period of time. And this speculation arises from a place of reasonableness. Everyone is recognizing that AI companies are running out of training data, that the open web is increasingly not as open anymore to AI products and AI crawlers. And so what do companies do? And I think the speculation has been that AI companies will now turn to synthetic data, which will lead to the self-improving cycle. This is very interesting because we've also at the same time seen issues with model collapse. I think just yesterday, Nature released its somewhat controversial paper on model collapse, which basically says that as you start training models on their own outputs, the model's quality substantially degrades. I think the truth is somewhere in between. So, we can use synthetic data for some domain-specific improvements. We have seen time and time again, we can use it for alignment tasks, we can use it for eliciting preferences. But at the same time, I think model collapse thinks about or looks at this as if we're not having any human intervention or filtering that's going on in between. And that's not really true, right? When companies are developing training data, there's a lot of human input that goes into how the filtering takes place. And so we cannot just assume that, all data is Gaussian and that's everything we'll use to train the next generation of models. But as far as it comes to synthetic data being the sole source of pre-training data for next generation models, I'm quite bearish on that working out.
I don't know if you saw, but there was a piece in Forbes yesterday, and they surveyed a whole bunch of people working in corporations, and 77% said that AI only complexified their jobs and, was basically giving them more stress in their day-to-day existence.
I do not find that surprising, frankly. I mean, To be clear, it might not be the case that AI is making the jobs worse. It might just be the case that there are organizational dynamics that are also changing as a result of AI being introduced into ARCs. And so it might turn out to be the case that this is temporary. But I think this also highlights this other trend we've been seeing with the introduction of generative AI and LLMs, which is that there are a lot of externalities that AI companies themselves don't have to bear, but that are imposed on other institutions. So in corporations, these are corporations that are using AI for profit-driven reasons, so perhaps that's okay. But when it comes to institutions like schools, I genuinely believe that AI has a place in our curricula. I genuinely believe that if students are taught how to learn AI well, it will be extremely useful for their future careers and for their thinking and writing skills. Many people say we should have none of it. I quite strongly disagree with them, in fact. But the fact remains that the introduction of ChatGPT-like tools has completely upended the curricula that somewhat already overburdened teachers were already having to deal with. And so basically, we are in this state where a lot of organizational and institutional practices are changing. And so some of the 77% of workers who said AI causes more stress might be reacting to these organizational dynamics much more so than the introduction of AI itself.
Does ChatGPT make kids dumber or smarter?
So ChatGPT definitely makes me a lot smarter in my day-to-day. I would say half of the first draft of code that I write is now generated using a language model. And that is saying something. I think for a lot of the recent work I've done, I've had to write a lot of code. And the fact that I can sort of operate at a higher level of abstraction for the large part of writing code, that really does change the equation dramatically for me. The other place where I really like to use tools like ChatGPT is where the outputs are easily identifiable. So you can easily verify if an output is correct or not. My website is generated using ChatGPT. My resume is generated using ChatGPT. Any place where you can easily verify the tool works or the output is correct is a great place to use it.
Yeah, I agree with your take. I talk about the understanding credit card quite a lot with ChatGPT, and I find if I already understand something, then it's a great time saver. But if I'm trying to understand something I don't yet understand, then it's not. Anyway, you have written this really interesting paper on AI agents, and maybe we should just start by saying, we've been talking about agents and multi-agent system, distributed systems, serverless for years. There's always big hype trains around technology. Do you think AI agents are different?
I think it's hard. It's very hard to say that AI agents. It's very hard to evaluate the state of agents at this point, to be honest. So far, what we've seen and what the paper was reacting to was that on the one hand, we have claims that AI agents work really well for tasks like coding or answering questions, factuality, and so on. And on the other hand, when these agents have been deployed in the real world, they have yet to make as much of an impact. So we were trying to square these two very sort of different results in some sense and trying to see what goes on. And the paper is somewhat cheekily titled AI Agents That Matter, because we think that most AI agents that are deployed right now don't. And so we looked at why that is the case and found that there's a bunch of standardization and reproducibility errors. Many of these agents that are deployed in research settings might not work in practice because they're just too expensive to run. And ultimately, we just need a better state of AI evaluation to answer the question in the first place or even contemplate it.
Yeah, so you found that simple baselines often outperform more complex agent architectures. Can you tell us about that?
Absolutely. This is one of my favorite findings from the paper. So my co-author and my co-lead, Benedict, and I were looking at human eval, and there had been claims that human eval is basically the top 3 leaderboard agents are all complex agents. They reflect on their outputs. They do some sort of debugging, and that's how they get to this impressively high performance. And what we tried to do instead was just to retry the outputs of an LLM multiple times. This is not doing anything fancy. There are some example test cases that are part of every human eval problem. If an LLM fails to pass these test cases, you just hit the reset button and retry again. And what we found that this simple trick is enough to essentially match the state of the art when it comes to agent designs. So a lot of the community wisdom around agents seems to be centered on the fact that we can do reflection and reasoning and this type of sort of system 2 thinking, if you will. And that's what gets agents to perform at a certain level. But we are essentially challenging that hypothesis. We are saying, like, look, if we just retry it 5 times, there is no system 2 here. And so what's going on here? And I think it also pushes us in the direction of understanding agents better. Is it really the case that there's reasoning going on, or is it just the fact that you have more tries, more tokens? But yeah, I mean, basically, empirically, it does seem to be the case that retrying is an exceptionally solid baseline, and that anytime you say that a complex agent architecture is needed, you must first compare it to a baseline, which essentially might cost like tens or hundreds of times lower. And that's the way to make meaningful comparison.
Yeah. So the cost trade-off was a huge theme in the paper. How do you jointly optimize cost and accuracy in agent design?
So I'm a big fan of DSPy. DSPy is this framework by Omar Khattab and others at Stanford and Berkeley that tries to optimize language model pipelines. It basically automatically tunes the prompt using language models, trains the model to input a few short examples that work best, and so on. And Benedict and I are both big users of DSPy. So the way DSPy works is that it tries to find few short examples and instructions for a given task. So let's say you want to solve a question answer problem that does retrieval augmented generation to answer the questions. What is the search query that you want to use in the retrieval system? What is the prompt to the language model? What are the few short examples that you should give to be able to generate nice search queries? One way to do that is by optimizing for accuracy. So you can optimize on a large number of synthetic or manually created prompts and few short examples, and that leads to you finding the best possible prompt. And you use that, and perhaps in the production setting it does well. So Omar has shown that DSPy is really, really good at finding these prompts that work way better than the current state of the art. They can improve the performance of like small models like Llama 8B to essentially match competitively with GPT-4 level models. What we wanted to do was we wanted to jointly optimize cost as well as accuracy. So instead of accuracy being the sole metric by which we evaluate how well a given prompt and a set of few short examples work, we also wanted to look at how much it costs. So what is the token length, and can we reduce this token length without taking hits on accuracy? So we modified the DSPy framework to work also with the token cost of an LLM call. And like the specific optimization was very simple. It was like a discrete optimization method we implemented. We are sure we can do better. But what we found was essentially just implementing the simple method we came up with can reduce the cost by half while still maintaining accuracy. So now you can have like Llama 3 level models or like basically essentially matching GPT-4 at like 1/10 the cost.
Amazing. What's the distinction between model evaluation and downstream performance?
That's a great question. So model evaluation is like evaluation that we all do with like language models to evaluate how well a model can solve a reasoning task, how well it can solve, let's say, a math task, a coding task, and so on. And the purpose of model evaluation is to compare two models against each other. It could be to compare if models have improved in capabilities as a regression test to see that models don't degrade version over version, and so on. On the other hand, downstream evaluation is completely different. So downstream evaluation is evaluation from the perspective of an end user who might be using a system based on this language model to perform a specific task that they are actually interested in. So as an analogy, I think an engine developer like Rolls-Royce building airplane engines might be conducting model evaluations when they're the equivalent of model evaluations when they're regression testing their systems. But Boeing, when they're building their aircraft, are interested in how well the aircraft as a whole performs. They do not really care about whether like a specific model has like the high throughput or whatever, insofar as that's their end goal. That's not their end goal, really. What they really care about is the performance of the overall system. And I think the same holds true for AI systems as well. So a person making a search engine using an LLM should care about whether the search engine has desirable properties, not whether the model itself has high reasoning capabilities. The somewhat sad thing is in the community, I think we've tended to conflate model evaluation with downstream evaluation. So in many cases, we see model developers claiming that their models are better at downstream tasks, And let's say they're more cost efficient than at downstream tasks, when actually what they should be comparing is what do the downstream metrics really reveal? How much does it actually cost? So one egregious example of this is Mistral's branding of how well their models perform. So I'm not sure if you've seen this, but every time Mistral releases a new model, they essentially come up with a Pareto curve. On the y-axis is like the MMLU score. On the x-axis is the number of parameters. And I think that's where the real sleight of hand happens. Because downstream users have like no interest in what the number of active parameters in an MOE model is. And so Mistral essentially claims that, in the Mistral 8x7b model, the number of downstream parameters is less than the number of downstream parameters in Llama 213b. But when you look at the costs of generating tokens using both of these models, Llama 213b is way cheaper because it has fewer memory requirements and so on. And that's the essential metric that model developers are often missing when it comes to the actual cost of running models. And we've seen this repeated in many cases. Sometimes it makes sense to sort of have different cost estimates. So if you are actually interested in the compute efficiency of your model training runs, then it makes sense to replace the cost axis with the number of flops, for example. But from the perspective of downstream users, this is rarely the case. Like the main bottom line metric for most downstream users is actual dollar cost, and that's the thing that's often ignored. Now, there are good reasons for ignoring this as well. Downstream costs for the same model might go down over time. Some models might never be made available again. There might be sort of changes to the price of a model depending on which provider you use it from. So like Together has a different cost from any scale when you use Llama models. I think despite these issues, it's still worth looking at cost, because in all of these cases, like the price is going down over time, for example, this actually meaningfully changes the experience of a developer. And so if we do want to measure like how a downstream developer would react to prices going down over time, it really does matter if providers are reducing costs, if compute is getting cheaper. And so in some sense, I would say it's a feature and not a bug of evaluating cost. And that's using that as the main metric for downstream evaluation.
You also spoke about the dreaded shortcut problem in metrics. Tell us about that.
Absolutely. So shortcuts have been like a problem for ML research for a long time. There's a great paper that I really like called Shortcut Learning in Deep Neural Networks, which basically shows how neural networks are likely to take shortcuts, relying on the color of the background for identifying species in an image or whatever. And in the paper, we point out that agent evaluations are extremely prone to shortcut learning. And in particular, that's because when it comes to agent evals, we've sort of given up on the principles of good evaluation. So one of the sort of standard principles of building an ML evaluation is having a held out test set. I think this assumption has led the ML field forward many times over in the last 50 years. David Donahoe at Stanford calls it the miracle success, and basically attributes all of this miraculous success of ML to the fact that we have this common task framework and held out test sets. When it comes to agent benchmarks, we basically looked at like over a dozen benchmarks, and in most cases, there is no held out test set. Now, there are many ways that agents could abuse this type of lack of held out. The simplest way would be that we build an agent that has access to a lookup table with the solution. You can actually do that today, just like feed in all of the answers into a hash table. All the agent has to do is retrieve the answers. That would be a legitimate solution to many of these agents. Now, of course, this is an exaggeration. Like no agent developer is going to do that. But there are many subtle ways in which agents can learn to do that, even if we don't explicitly feed it in. They can be human in the loop overfitting, as some people call it. So we sort of tweak our agents until they get a very high accuracy on a benchmark. But all that's doing is feeding in the test set and information about what's in the test set. So this is like one of the main challenges with evaluation. There's also the challenge of having a held out set at the right level of generality. So in many cases, people are claiming to make domain general agents, like web agents that can basically do anything on the internet. But when it comes to these web agents, I think the task of creating a held out test set becomes even harder. Because you might have cases where, let's say, a web agent benchmark has 8 different websites, like an e-commerce website and an email website and a travel planner. and a coding website, and so on. But if all of these different types of websites are made available and like the agent developer knows which precise websites are included in the benchmark, then already like half of the challenge of the open web is sort of circumvented. Because on the open web, the agent would never know what clicking on a link will lead to. They might be led to a completely different website that's not in their domain. And so when we are making statements like we have built generalist web agents based on these sort of very specific agent benchmarks, we are likely to be misled into thinking we have extremely useful and capable agents, whereas in reality, these agents might not work well at all.
Yeah, I mean, quick aside, I love that shortcut learning paper. Everyone at home should read that paper. It's absolutely amazing. We should be thinking more about the spectrum of non-robust generalization. But you spoke about the lack of standardization in agent evaluations as well. Can you talk to that?
Absolutely. So one of the things we found out when we were conducting these evaluations is that many evaluation benchmarks do not come with like a standardized way to evaluate on the benchmark. So you might have a benchmark with like 1,000 tasks, but all the benchmark developer is providing is the list of tasks. How to conduct evaluation on those 1,000 tasks is left up to the agent developers. Now, what this means in practice is that an agent developer might skip some tasks. They might sort of remove 5 tasks that they feel are like not working or have some issues. They might change the tasks. So since the tasks are available openly, they might sort of modify the tasks to change the structure, change the order. And we've seen that LLMs are extremely sensitive to how information is presented to them. Prompt sensitivity is a huge issue for evaluation. So when we give agent developers all of these degrees of freedom, in a way, we're also diluting the impact of these evals, because when 2 agent developers say they have a certain accuracy on a benchmark, that does not mean the same thing.
Okay, and the other thing is, this is really important. You spoke about humans in the loop. Can you bring that in? How important is that?
Yeah, absolutely. So, I mean, I think humans in the loop can both lead to overestimating as well as underestimating the capabilities of AI agents. So they can overestimate the capability. Like I mentioned, they can be human in the loop overfitting. A human is literally coding in, even indirectly, all of the tasks in a benchmark test set into the agent, and that makes for artificially high performance. But I think something that's often missed is that humans in the loop can also lead to us underestimating how well an agent can do in the real world. And that's because when you think of yourselves using like an AI agent like GitHub Copilot, we're always in the loop giving it feedback. So if there's something that's obviously wrong, we can say, maybe that doesn't look like right, try again. So, and what we've done with that one sentence of feedback is we've turned pass at 1 accuracy into pass at 2 accuracy, which are like dramatically different for AI agents. And we've repeatedly seen that retrying multiple times is an effective way to drastically improve accuracy. Now, one of my favorite examples of this is a qualitative study that was done by my colleagues at Princeton University, where they looked at the USACO benchmark. It's a coding Olympiad benchmark based on real problems from these Olympiads. And they looked at a small test set of like about 15 problems, I think, where a human could provide some basic rudimentary feedback to an LLM agent based on where it went wrong. GPT-4 and most other models had an accuracy of close to 0% when there was no feedback from a human. When there was feedback from a human, the accuracy of GPT-4 went up to 86%. And mind you, this is very simple feedback in the form of like just general steps about like things an agent can do. And so this basically shows how important it is to not just treat AI agents in a vacuum, to not think that they're operating without any human assistance at all. And this is an example of how we can underestimate the capabilities of agents if we don't involve humans in the loop. Now, of course, human in the loop studies are extremely expensive. There are lots of challenges to doing them right. We have like entire fields of social science research that tell us how we should do these types of things while still maintaining validity. But essentially, at the end of the day, if our job is to measure how well tools work in the real world, then one of the best ways to do that is through human-in-the-loop studies.
Very cool, very cool. And final question, you spoke about different levels of agent generality. Can you bring that in?
Absolutely. So I think when we're talking about AI agents, we might be talking about very different types of agents. One example of an AI agent would be SWE agent. It's an agent also developed by others at Princeton, which aims to solve software engineering tasks that are created using GitHub issues. This is a task-specific agent. So there's a specific task that the agent is made for, which is solving GitHub issues, that is given a description of a particular issue and a repository, make a change to this repository that fixes this issue. Then there have been claims that we have more general agents. So one of the claims that we've seen repeatedly in the last year are about domain general agents on the web. So these generalist agents are claimed to operate on the open web. They can essentially do any task on any given website. And this is fundamentally different from SWE-bench because the tasks now have no structure. There is not like a singular task that an agent must be able to do. Rather, it needs to learn to operate in many different types of environment. And finally, at the highest level, we have tasks that are completely general. So an agent must be able to do, let's say, tasks related to the web, tasks related to coding, tasks related to robotics, essentially close to some definitions of AGI where people feel like we have completely general agents that can do most tasks similar to how humans might do them. And at these three different levels of granularity, I think the types of benchmarks we construct also need to be extremely different. So for task-specific agents, what we really need is to model how these tasks might change over time. And that's the basis for actually creating the test set. That's the basis for actually creating like the evaluations that we use our AI agents on. Because if you think about solving tasks like the SWE-bench series of tasks, it's not like code repositories stay stable over time. The types of issues change, languages change. In some cases, repositories go out of business, other repositories come in. And so what we really need to model is how well does an agent sort of do when these types of changes are included in the task. On the domain general level, we don't just need different tasks in the held out test set, but we need like entire websites that were not, for example, in the held out set of a web agent benchmark, because that's the only way in which we can actually model how, let's say, a generalist web agent would do when exposed to new types of websites in the real world. Now, what this also means is that we need to improve our standards for how we release benchmarks, because what I'm essentially proposing here is that a specific portion of the benchmark should always remain secret. Like it's not just that a certain type or a certain set of websites is declared to be the test set. It's that we need to have like a held out test set that's completely secret for the duration of its life. This is the approach that we've seen fail many times in the ML community. There's a strong culture of openness and perhaps rightly so in the past. But I think this is an approach we have to adopt if you're concerned about issues like LLM contamination, where an LLM might literally be trained on the test data and therefore overestimates the performance.
Yeah, this is a secret that Francois Chollet knows all too well. do you have any quick comments on the ARC challenge?
So I think the ARC challenge is very interesting and fascinating, specifically because it tries to model this type of distribution shift. So one of the sort of most important parts of the paper on the measure of intelligence that I think is often buried is that Chollet comes up with this entire hierarchy of intelligence. Like, are you just sort of learning in distribution examples? In which case, I think he would be pretty optimistic about any system development happening on that level. Or are you learning out of distribution samples? And at what level are these out of distribution? And I think actually this paper was a huge inspiration for us as well when thinking of this hierarchy of generality. When it comes to the ARC test set specifically, I think there are two types of claims to be made about it. The first type of claim that I've seen online is that progress on ARC means progress towards AGI. The second type of claim is that ARC is like one specific domain. You can create like a domain-specific language, and actually that's how we've seen most of the leaderboard competitors do well on it. I lean towards the latter view. I think AGI is something that is sort of much more open-ended compared to even the set of tasks that ARC has. So, I mean, maybe progress on ARC is progress towards like verification systems that work better, and maybe verification systems and DSLs are what we need for AGI. Both of those are like relatively tenuous claims, but I do think that like ARC is in general one of the more well-designed benchmarks. And at least when it comes to evaluation designs, we should take a lot of lessons from how ARC thought about its held out sets.
Yeah, and to be fair, Cholet would agree with you. He thinks it's a necessary but not sufficient condition. I think there's a difference between Cholet and the organisers of the ARC Prize. But anyway, Sayash, it's been an absolute honour to have you on. This has been one of my favourite interviews all week. And folks at home, subscribe to the AI Snake Oil Substack blog, pre-order the AI Snake Oil book, and thank you so much for coming on.
Thank you so much for having me.